introduce our next speaker from Stony Brook, Vladimir Korepin, and again, he was involved in these early developments, as we saw, so it's a great pleasure to hear him speak about Yang-Baxter equations and Clifford algebras. Thanks, Vladimir.
Thank you for inviting me. I'm honored to celebrate the life and achievement of Professor Baxter. So Clifford algebra has generators, which I denote by gamma here. We denote it. I have a quote from Professor Padmanabhan. So generators of Clifford algebra anti-commute and square to plus or minus 1. So this A and B will be just elements of Clifford algebra, which are some products of some generators. For the example which I considering for the start of the lecture, A and B supposed to anti-commute. And then I will have several different vector spaces like lattice sites, and those lattice sites will be labeled by lower index say I and J. So the operators in the different vector spaces, different lattice sites commute as usual. So let's try to construct solution of Yang-Baxter equation using this Clifford generators. So let's start with Yang-Baxter equation, then we'll proceed to a tetrahedron equation and other high equation. So first of all, this is our Yang-Baxter equation written in the standard notation. It's already appeared here in such a form. I think Professor Witten wrote this in such a form. So first of all, if R, so R here acting in the site number I, the site number J. If we just make an ansatz like separable product, so one matrix in one lattice site and the same matrix in the other lattice sites, it's trivially satisfy Yang-Baxter equation. So both sides of Yang-Baxter equation reduced to this expression, squares of each I. So this is evidently a solution, kind of trivial solution. Same for B, factorized solution. Okay. Let's proceed. Let's take the linear combination. So this is famous picture, which everybody knows here. Let's try to take linear combination of those two, AA plus BB. Will it work? Well, I mean, this is the left-hand side of Yang-Baxter equation. This is the right-hand side of Yang-Baxter equation. And then to transform left-hand side into the right-hand side, I have to make several transpositions. Each time I move A through B, I get some minus signs. On the other hand, there is even number of transpositions, so minus 1 eventually gets squared to plus 1, and the left-hand side is identical to the right-hand side. So this is the solution. And actually, coefficient, I can change coefficients in front of A and B by some complex numbers. So this is just a solution. Does it work for high dimension? Does it work for tetrahedron equation? Okay, this is a tetrahedron equation which was suggested by Zamolodchikov, and there is several different forms of writing this tetrahedron equation: vertex form, edge form, and self form. So let's try. This is the R matrix which is supposed to satisfy tetrahedron equation. Let's try our factorized form, the same matrix in 3 different lattice sites. It does work. It satisfies tetrahedron equation, kind of trivial solution again. I can change this. Instead of 3 A's, I can take 2 A's, one B, 2 B's, 1 A, and 3 B's. Each of these satisfy tetrahedron equation kind of trivially. Let's proceed. Let's try to take the linear combination. So alpha, the red one, the alpha, beta, gamma, and delta are some complex numbers. I put this in the tetrahedron equation, make those transpositions. There's even number of transpositions again. So the minus 1 gets squared. So this is solution. This is solution of tetrahedron equation. These coefficients, I can make these lattice dependent, and actually I can announce that this is spectral parameter, multi-dimensional spectral parameter, kind of simple dependence, but it's just a point of view. Let's proceed further for higher simplex equation, n equal to 4 simplex equation suggested by Professor Bazhanov and Stroganov. For higher, this is a simplex equation in a higher dimension, more indices. Well, I can try the trick which already worked for lower dimension. Maybe R is equal to the product of all 4 A's in the different lattice sites, or maybe two A's, two B's, or maybe four B's. Somehow even number will be important later. I will comment on the red color later as well. Those I put this in the equation, and it trivial identity to the both sides. So it does solve it straightforward, similar to the way how it worked for Yang-Baxter equation. How about linear combination? I can take linear combination of those kind of even type with different complex numbers. I put this in equation, make my transposition, and it works. It satisfies this simplex equation. How about high? N is the dimension of the space-time. So I adopted Baxter point of view. So this is I'm considering the space in n-dimensional lattice in the n-dimensional space, and these R entries, matrix elements of R, are Boltzmann weights. So n is a dimension of the space. So let's try our trick with factorization. Let's take several A's and several B's and try to put this into the highest simplex equation. Well, there is a condition. So the A's, A small was indexes of A. And then as long as any difference of couple of A smalls is even, then it works. It satisfies highest simplex equation. Well, in principle, I can also take linear combination. Well, as long as I keep this even property, then it works. It also works. I can take linear combination. So there is something else. So now I'm kind of changing the subject a little bit. Remember, in this simplex equation, I had black and red. In red, black has two A's, two B's, but there was also red, which was even numbers A and even numbers of B. What happened with those? Those satisfied kind of generalization of Yang-Baxter equation with minus sign. So it's not Yang-Baxter equation. I can say that twisted Yang-Baxter equation because it has minus sign in the right hand side. So we call it the anti-Yang-Baxter equation, and it does lead to integrable models for the even lengths of the lattice. If the length of the lattice is even, somehow this minus one cancel, and we have our conservation laws. Also, we shall consider tetrahedron equation, for simplex equation with a minus sign. So we have those red ones, three for tetrahedron equation, 3 A's and 3 B's. So those well, I can take put this in the equation, anti-Yang-Baxter, and it works. It goes through. This is the identity, some kind of working identity which we use in our derivation. Now, also a reflection equation. This is some step forward, except of Yang-Baxter equation. We can consider open boundary condition and the reflection equation, which was introduced by our colleague Evgeny Sklenin, and later generalized to many dimension by Professor Kuniba. So, except of Yang-Baxter equation, there is also a reflection equation, which contains this matrix K, which describes reflection of the wave from the wall. So remember, my solution of Yang-Baxter was A plus BB. If I take for K sum of A and B, it works. So this reflection algebras also can be satisfied by Clifford algebras. Even in higher dimension, if I have n equal to 3 Ks, this is a solution of tetrahedron equation, which I discussed in the beginning. And K, the reflection matrix from the wall, which should satisfy this equation. I think it was derived by Professor Kuniba. And the K is 4A's plus 4B's. So Clifford algebra also happens to solve reflection equation. So this was kind of a general consideration, general construction. Let's consider I mean, like general algebra. Let's consider some kind of specific representation matrix solution for the low dimensional space. Let's take V, the local space, to be C2, and XYZ will denote Pauli matrices. So, from our point of view, two A's and two B's, right? So let's take sigma x plus sigma z with some coefficients. That's a solution of Yang-Baxter equation. That's not new. It was known. I read this in Hitarinta, but we can reproduce it. The other solution, we can take a sigma minus for A and sigma z for B. Those also anti-commute, so Clifford algebra, and take another solution. So in such a way, we reproduce another known solution of Yang-Baxter. For tetrahedron, we can take this x, z, z, and this is solution of tetrahedron, which is kind of new. And then for another example for tetrahedron, we can take sigma plus and sigma z and write this kind of triangular solution of tetrahedron. And this is examples. Those are examples of the Clifford algebra. So now I hope I still have some time because it's like approximately half of my lecture. And then this is the end actually of our Clifford approach. We have two other approaches for solution of Yang-Baxter equation. I'm switching to other ones. So except of Clifford, we have two other set of solutions. One is Susy, supersymmetry, and second Majorana fermions. So let's briefly comment. Brief solution. So Susy, I have to, we're considering nilpotent matrices, Q square equal to 0. And then we use some notation which coming from supersymmetric quantum field theory, usually anti-commutator of Q dagger denoted by Hamiltonian. And this is like some notation. So this is algebra. We can consider representation of algebra, of this algebra in terms of two-dimensional matrices. If we do that, then this formula will give us a permutation operator, which is a solution of Yang-Baxter equation. And then later we can use Baxterization. I will explain next round, remind Baxterization in the next solution. And this will reproduce famous Young solution, which was the first solution of Yang-Baxter equation. On the other hand, I can take high dimensional matrices. For Q, I can take three-dimensional matrices or four-dimensional, high-dimensional matrices. Of course, there's a lot of nilpotent matrices in high dimension. And then this formula will give new solution of Yang-Baxter equation. The way I wrote it doesn't depend on spectral parameter, but I can use this Baxterization and get some new solution of Yang-Baxter with a spectral parameter. So let's proceed. So Baxterization was developed by Professor Takhtajan, Reshetigin, Sklyanin, and Kulish long time ago. This is some formal method, which I probably don't have time to discuss. So we can use this method, Baxterization, for our case, for the case which we discuss. And then we can reproduce new R matrices, solution of Yang-Baxter equation. Some of them will be invertible, some will be non-invertible. And the Hamiltonians, which will come out as a logarithmic derivative of our matrix, majority of them will be non-Hermitian. On the other hand, non-Hermitian Hamiltonian has an application to condensed matter, because in condensed matter, system interacts with the environment, and non-Hermitian Hamiltonian fit well for the description of the interaction of a system with the environment. So this is like, there is some publication with more detailed consideration, so I'm giving a hint because of the lack of time. So the third approach, it's our third approach for solving Yang-Baxter equation as well as high simplex equation. Let's consider Clifford algebras. Gamma generates of Clifford algebra, delta is a Kronecker symbol. So if I take this R, identity plus three gammas, this is this Majorana. This is a solution of tetrahedron equation. We put it in, there is minus sign until commutators works out. This is solution of tetrahedron equation. All right, and there are more details in this paper. I sent the files, PDF file of my lecture to the organizing committee, so if you're interested, you can click on the link. This Majorana equation, Majorana approach, our Majorana approach, we can fit Ising model and Hubbard model in this Majorana approach. So we can reproduce known results for these models. Yet another application. Of course, so far I was going along traditional lines. We have Yang-Baxter, we have Hamiltonians, integral models. On the other hand, there is a new application. So I can consider quantum circuits, and there is a gate, and I can use solution via Yang-Baxter equation at a gate in quantum circuit. There are several references. This leads to the new direction, which is called completely integrable quantum computers, which has some properties. This is kind of, I want to approach closer to the end of my lecture. So summary, what I explained in my lecture, I think that Clifford algebra provide us a method of solving n-simplex equations, starting with Yang-Baxter's and higher. We also solve this anti-Yang-Baxter equation with a minus sign in the right-hand side, which I said lead to integral models for the even lengths of the lattice. We also solved also reflection equation, and we have two, except of Clifford, we have two other approaches: SUSY, supersymmetric algebras, and Majorana. I also want to emphasize the role of my co-author, Professor Padmanabhan from Indian Institute of Technology. Thank you for your attention. That's the end of my lecture. Thank you.
Okay, thanks, Vladimir. We have plenty of time for questions. Do we have any? Yes. Vladimir Korepin has a question here.
Can you reproduce 6-vertex model in this approach?
6-vertex model. I don't know. It's probably special case. I think we can reproduce special cases of 6-vertex model. I mean, my co-author is in here, so let me ask my co-author. Pramod, I think we reproduce special cases of 6-vertex model, not the full 6-vertex model.
Yeah, so I think so the answer is from the SUSY approach, it is possible to
from
obtain
SUSY, SUSY. Vladimir Bajan from the SUSY, it comes out from SUSY. Supersymmetric algebra, those nilpotent matrices, Q square equal to 0.
We have any other questions online? Quite an audience there. I know that Atsuo Kunaba is watching, for example.
Instead of sitting here.
I got a question.
Oh, Remy.
So can you use this method for a generalized Clifford algebra for like parafermions or more than nearest neighbor?
You know what? You remember my anti-Yang-Baxter with a minus sign in the right-hand side? Minus sign appears as a square root of 1. If I, instead of the minus sign in the right-hand side of Yang-Baxter equation, if I put cubic root of identity, then it also works. It will be like more generalized, twisted Yang-Baxter equation. We also have solution and also work. If the length of the lattice is divisible by 3, it will produce exactly solvable spin chains. So that's our point of view to your question. I mean, maybe Pramod has better answer. Pramod, do you have better answer?
Yeah, so it is possible to use like generalizations of SUSY algebras. So like we can use para-supersymmetry or like parafermions also to construct solutions. And it will give models which are not nearest neighbor. So like we can get, so it's something similar to what Post guy was talking about in like yesterday's talk. So like we can get like local, quasi-local, and global integrable models with these approaches.
All right.
Yeah, that's very interesting. Me personally, I've never heard of this negative Yang-Baxter equation. Does that have any sort of Well,
Well, I mean, the way it approach, we have our like A, B, B, and then this red one didn't fit in the solution of Yang-Baxter equation. So maybe it solved something else, and then this anti-Baxter came out because of the structure of our solution. Then we realized that conservation laws, the method which Professor Takhtajan explained, quantum inverse scattering method, will work for anti-Yang-Baxter in the case if the length of the lattice is even. So it's like good enough with some restrictions. That's we kind of, found kind of randomly. I mean, Pramod, do you have better answer?
No, so I mostly agree with you. So it is also possible, instead of having a negative sign, I can have something like an alpha. Okay, and it'll still be like consistent with the RTT like relation, the intertwining relation. So it is possible to obtain integrable models on all kinds of spin chains, where the number of sites can be even or a multiple of 3 or any multiple of some integer. So we can put the kth root of unity instead of a negative sign.
I agree completely.
yeah, that's very interesting.
Thank you.
Yeah, I'm sure Rodney Baxter would be very pleased to see so much life in the Yang-Baxter equation.
Thank you. Thank you. That was the idea.
So, are there any further questions here, or if not, then we'll thank Vladimir for a very nice talk.
Thank you. Bye.
Thanks a lot, Vladimir.
Bye.